Welcome back. So here's another goodness of fit example. In his book Outliers, Malcolm Gladwell claims that more hockey players are born in January through March than in October through December. The following data show the number of players in the National Hockey League in the 2014-15 season according to their birth month. Is there evidence at the alpha equals 0.05 level of significance to suggest that professional hockey players' birth dates are not uniformly distributed throughout the year? So we've got an observational set of data here. 278 players were born January through March, 246 April through June, 163 July through September, and 143 October through December. So we've got the year broken down into 4 quarters. We've got number of hockey players born in each quarter, and we want to know if this data frequency distribution matches the uniform distribution. Now obviously so uniform meaning same number would be in each category. Now obviously it's not the same number in each category, but are they far enough off that at the 0.05 level of significance can we say that, oh, they're so far off that no, we don't think the birth dates are uniformly distributed? Or are they not so badly off the uniform distribution that maybe we don't have evidence to reject the uniform distribution? Okay, so our hypotheses, the null hypothesis is always that the observed distribution matches the specified one, which in this case is the uniform distribution, so that they're evenly distributed. So let's just say birth distribution is the uniform distribution. And our alternate hypothesis then is that the birth distribution is not the uniform distribution. Now to make that a little bit more mathematical, saying that the birth distribution is the uniform distribution means that you have the same number of players in each category, and that means the probability of each category is the same. So another way of saying this, and you'll see this in the textbook, another way of saying this is that probability of category 1 is the same as probability of category 2, which is the same as probability of category 3, which is equal to the probability of category 4. Saying that the birth distribution is not the uniform distribution, another way of saying that is that at least one of the p sub i's is different than the others. Okay. By the way, if there are 4 categories equally weighted, equally distributed, what's the probability of each one? So if there's 4 categories that a player's birth date could land in, and there's an equal likelihood of landing in each of the 4, what's the probability of any one of them? Yeah, it's going to be 1/4. Okay. And then based on that, let's just note also that means that the expected count for each category, so I'll just say E sub I instead of doing this 4 times. Remember, that's probability of that category, which is 1/4 for all of them, times the number of trials, so the number of individuals that were sampled. And do I have a total there? Yeah, so if you add up the four numbers, you get 830. Okay, so there's 830 hockey players whose birthday was checked. Okay, and that works out to 207.5. The test statistic would not be bad to compute by hand, but let's make our life easier and get some practice with the spreadsheet. We'll do that in the next video.